For this example, we're going to be sketching a solid that's bounded by some surfaces, and then we're going to use that sketch to set up an iterated integral for the mass of that solid. And if you look at the equation for the mass of the solid, that's where we're going to use this density function here. But for the first part, when we just want to sketch that solid, there's three things that we want to consider. One is this surface here, z equals square root of x squared plus y squared. And then we've got the plane z equals 2. And then the third thing we want to realize is that it's only in the first octant. So let's go through those one at a time. First one, we're saying that z is equal to square root of x squared plus y squared. And if I square both sides, I get something that might be a little bit more recognizable. So when you learned how to sketch quadric surfaces, you might have come across something like this. But when you square both sides of the equation, you're losing a little bit of information. And the information that you're losing here is that z is equal to something underneath a square root. So we need to say that z is greater than or equal to 0. So that's kind of in addition to this equation. Just taking one extra step to rearrange it into something that you might be able to identify from quadric surface sketching. This is going to be a cone, and you can refer to your notes on sketching quadric surfaces, or I have a more detailed write-up for how I came to this conclusion, but this is a cone, and it's going to be along the z-axis. Because I've got that negative sign out in front of the z squared. And then I still need this piece of information that tells us that this is just the top half or the positive z values of that cone. Z equals 2 is just the plane of the floor, the xy plane, moved up 2 units. So that one will be pretty straightforward to sketch. And then we also have the information that it's in the first octant only. And what that's telling us is that we're only using positive values of x, y, and z. So we'll say that both x, y, and z have to be greater than or equal to 0. Okay, so let's sketch this. I'm going to start off with the cone. So that's going to look something like this. Okay. That's my cone, and then it is bounded on top by this plane z equals 2. So we can kind of imagine z equals 2 cutting that off right here at z equals 2. And then the last piece is that it's only in the first octant. So that means that we're only looking at positive values of x and y. Z, it's already positive. So we're going to kind of cut off 3/4 of this cone so that we're only looking at this piece here, and I'll shade that in sort of a blue shade. Right, so we're only looking at this quarter of the cone that's in the positive x and positive y section there. So that's my sketch. I want to think about if there's any important things I want to note about this. I think for now, I'm just going to note that this is happening at z equals 2. And then we'll see what other information we need. But I think this is good enough for now. Looks good. Okay. So the second part is asking for the mass of the solid, and the mass follows this formula here, where this piece is our density function. So it's a triple integral across x, y, and z, and then we have a density function in the middle here. First thing I'm going to do is go ahead and plug in that density function. So leave yourself lots of room for all these bounds in here. But our density function from the top of the problem is e to the negative x squared plus y squared. And another thing that I'm going to change here, so this is in the cylindrical coordinates section, and I want to define this in terms of cylindrical coordinates. So this dx, dy, dz converts to dz is going to stay the same, and then we have r, dr, d theta. So don't forget about that extra r in there. And this is the order that you're almost always going to want to use. dz, r, dr, d theta. Okay, so let's think about what goes here for our boundaries for this integral. Z, looking back at the sketch, it looks like Z is bounded between two surfaces, and we want to think about which one's on the top and which one's on the bottom. So I like to sort of picture something being dropped through along the z-axis. So kind of falling from the sky here, it's going to hit that 2 first, z equals 2, and then it's going to hit our cone. That's defined by z equals square root of x squared plus y squared second. So this is going to be our top surface, and that's going to be our bottom surface. So let's go ahead and put those down here. So on the bottom we have square root x squared plus y squared, and on the top we've got 2. Okay. The next one is dr, so that's associated with this one here. And r is measured just like it is in polar coordinates. So for this one, I like to think about what the projection or what the shadow is if you were to cast a light right, kind of from the top here. So there's a flashlight in case you can't tell what that's supposed to be. And the shadow that that's casting, or the projection onto the xy plane, is going to look like this quarter of a circle down here. So we want to figure out what the radius of this circle is. And there's a couple ways to think about this, but one really common way is to look at this top circle here. So whatever the radius of this circle on top is going to be the same as this circle down here. And this circle is occurring when z is equal to 2. So just by inspection, we can see from this formula here where it intersects with this cone that if z is equal to 2, we've kind of got the equation of a circle, x squared plus y squared is equal to 2 squared, or r squared. So if I quickly set z equal to 2 temporarily, then I'm going to get 2 squared equals x squared plus y squared. And using your polar coordinates, you can say that in this case your r is equal to 2 at that point. So if we want to talk about this region here of the projection, then the radius is going to be going between 0 and 2. So r is between 0 and 2. And then for theta, so theta is measured just like it is in polar coordinates off of the unit circle. But it's a little tricky sometimes to get this perfect in 3D sketches because you're probably used to seeing theta down here like this, where this is your x-axis and this is your y-axis. And it still works that way, but it's just, it doesn't intuitively look like the same thing down here. So remember, it's just coming off of the positive x-axis and rotating towards the positive y-axis. So in this case, we're sweeping a quarter of a circle. So this would be theta equals 0, and then that sweeps all the way up to here, which is that's going to be theta is equal to pi over 2. So we're kind of sweeping right that quarter of the circle. So theta is going to be between 0 and pi over 2. This step we can kind of generalize it to say this is setting up the bounds. Right, and you generally want to do this first. We're not quite done with this though. The problem that we have here, and you might have noticed it, is that this density function and some of our functions in here, we want to be integrating them with respect to z and r and theta, but we still have x's and y's in here. So in order to change that, we want to use those formulas that we have to convert from cardinal coordinates or rectangular coordinates to polar coordinates. So this first one here, we have that r squared is equal to x squared plus y squared. So this thing here is just going to be a single r. 2 can stay the same. I'm going to move this r out in front here, just so I don't forget about it. So here's my r. And then this piece is going to be e to the, I want to put this in terms of r and theta. Just something to think about. So I'm going to go ahead and write negative r here. But just so you're aware, you may be tempted. I see a lot of people, they know, for example, that x is equal to r cosine of theta, and that y is equal to r sine of theta, and so they try to plug in values for x and y in here. Just always be on the lookout. Whenever you can simplify this just by using r, that's going to be the best substitution that you can make. So here, the simplest way to write it is just r e to the negative r. I already took care of this r, so all that's left to do is write my dz dr d theta, and that concludes the solution.